This is section 6.6 and 6.7 of Honors Algebra 2, Real and Imaginary Numbers. We're going to look at some different sets of numbers, starting with the first numbers you ever learned as a child, what are called the natural numbers. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and we could keep going forever. What I'm interested in is whether or not these different sets of numbers are closed under different operations. To be closed means that if I take any two numbers in that set and I perform that operation on them, do I always get another number in that set? So are the natural numbers closed under addition? If I take any two natural numbers and I add them together, do I always get another natural number? Well, it turns out that yes, they are. If I take any two rational numbers, or any two natural numbers, and I add them, 3 plus 5, I'm going to get another natural number, 8. Okay? Are the natural numbers closed under subtraction? Well, I can take 4 minus 3, and that's 1, that's another natural number. But what if I take 3 minus 5? That's negative 2. Is that a natural number? No. So are they closed under subtraction? No. And I don't like that. I would love for my number system to be closed under subtraction. I love that if I could take two numbers in my system, I could subtract them and get another number in my number system. So how do we fix that? Well, we expand our number system so that they are closed under subtraction. In order to do that, I need to introduce the negative numbers. So we do that and we get the integers. We've got all the natural numbers and we've got their negatives. Okay, and they go infinitely in both directions now, positive and negative. Alright, so this is closed under addition, this is closed under subtraction, is this closed under multiplication? If I take any two integers and I multiply them, do I always get another integer? Well, yes, I do. Okay, negative 2 times positive 3 is negative 6, that's another integer. And I could do that, and I'll always get another integer. Are they closed under division? Well, 4 divided by negative 2, that's negative 2, that's another integer. What about negative 2 divided by 4? That's negative 1/2. That is not an integer. So no, they're not closed under division. I don't like that. What do I do about it? Well, I expand my number system to one that is closed under division. What would that have to be here? That would have to be any fractions of integers. Because if I'm dividing, I'm essentially creating a fraction. So I need to include any fractions that I could ever possibly form of any integers. That set is called the rational numbers. The rational numbers are the set of all fractions of integers. Another way to write that would be the set of all a over b such that a and b are integers. That's how I would write it in set notation. Take the set that I could form by taking any fractions of any two integers. So they could be positive or negative. Okay? That's certainly closed under addition and subtraction and multiplication and division. Is that closed under taking exponents? So if I take a fraction, like 2/3, and I raise it to a power, do I always get another fraction? Sure, absolutely, I get another fraction. Okay. And it could be any power, not just 2. I could raise it to a negative exponent. I'd still get another fraction. I just have the reciprocal, right? I could even raise it to the 0 power, and I get 1, and that's another fraction. Okay? Is it closed under roots, which is the opposite operation of powers, of exponents? So the opposite operation of squaring something is to take the square root. Are the rational numbers closed under taking square roots? If I take 2/3 and I take the square root of 2/3, do I get a rational number? I would get the square root of 2 over the square root of 3. But I don't know the square root of 2 or the square root of 3. They're decimals that never end and never repeat, so I cannot write them as fractions. So no, this is not closed under roots. It is closed under taking exponents, but it's not closed under taking roots. And I don't like that. There's actually a second problem with taking roots. The second problem would be if I take a negative rational number, like even something as simple as negative 4, and I try to take the square root of that. I've got even deeper problems that we're going to have to fix in a minute. So we'll keep that in the back of our mind. A little thought bubble. This is also a problem. But even if we're just restricting ourselves to positive rational numbers, we've got problems. This is not a rational number. So we expand our number system so that it is. The irrational numbers are the set of any non-terminating, non-repeating decimals. So I'm taking the things that are not rational numbers, and those are the irrational numbers. The rational numbers would be anything whose decimal ends or repeats. So the rational numbers would include things like 0.5, because I can write that as a fraction, it's just 1/2. I can write even 0.38 as a fraction, it's 38/100. Okay, even one that repeats, like 0.3 repeats, and that's 1/3. Even something more complicated, if I take 0.327, where the 27 is repeating every time. And this method will work for all of them. If I take that as a number, and I'll call that number n, what happens if I take 100 times n? Well, I'm going to get 32.727, and the 27 is going to keep repeating. So I just took my number and I moved the decimal point 2 places to the right. What happens then if I subtract n from 100n? I'll get 99n, and that would be 32.4. 7 minus 3 is the 4, and then the 27 repeating is always going to have a 27 below it to cancel out with it. So I just get 32.4. That means n is really just 32.4 divided by 99, which is 324 divided by 990. That I can simplify. That's 18/55. So I can take any repeating decimal and I can write it as a fraction, and the process would be exactly the same as that. Okay? So any repeating decimal is a rational number. Any terminating decimal, like 0.38, is a rational number. I can write it as a fraction. So the irrational numbers are anything that do not terminate, do not end, and do not repeat. What would that look like? Well, pi is an irrational number. Pi is 3.141592, never ends, never repeats. Turns out the square root of any number that's not a perfect square, any positive number that's not a perfect square, is an irrational number. The square root of 2 is an irrational number. The square root of 13 is an irrational number. The cube root of something that's not a perfect cube, the cube root of 5, is an irrational number. The fourth root of 7, the fifth root of 8, those are all irrational numbers. And there are an infinite number of irrational numbers. Turns out there's actually a greater infinity of irrational numbers than there is of the infinity of rational numbers, but that's a story for another day. If I take the set of rational numbers and the set of irrational numbers, so everything that can be written as a fraction of integers, and everything that consists of decimals that never end and never repeat, and I lump those two together, I get the real numbers. The real numbers are simply the rational numbers and the irrational numbers united together. Okay. Now this set, is this set closed under addition? Yes, I can take any two real numbers, add them, I'll get another real number. Closed under subtraction? Yes. Closed under multiplication? Yes. Division? Yes. Exponents? Yes. Taking roots? Well, we solved one of our two problems with roots. If I just have positive numbers and I take their roots, now I'm closed under the positive real numbers. But if I want to use negative numbers and try to take a square root of a negative number, or the fourth root of a negative number, or any even numbered root of a negative number, I cannot do it and get a real number. So they are not closed under taking roots. That's that second problem we had right up here. So how do I solve that problem? Well, what if I take the square root of -1 and I call that something, and I'm going to call it I. So I is the square root of negative 1. If I is the square root of negative 1, what is I squared? Well, I squared is square root of negative 1 times the square root of negative 1. But that's the square root of negative 1 squared, and that's simply negative 1. So I squared is negative 1. What's I cubed then? Well, I cubed is I squared times I. So that's negative 1 times I, or negative I. Okay? What's I to the fourth? Well, that's I cubed times another I. So that's negative I times I. That's negative I squared. I squared was negative 1, so that's negative of negative 1, which is 1. I to the fourth is 1. What's I to the fifth? Well, that's I to the fourth times I, but I to the fourth was 1, so that's 1 times I, and that's I. Turns out, this creates a pattern. I to the first isn't the square root of negative 1. So I to the fifth is also the square root of negative 1, or it's I. I squared is negative 1. I to the sixth is also negative 1. I to the third is negative I. I to the seventh is also negative I. I to the fourth is 1. I to the eighth is also 1. It repeats that same pattern of 4 numbers. I, negative 1, negative I, 1. That's cool. Turns out we can do other stuff. If we just call the square root of negative 1 I. Square root of any negative number then, in terms of I. The square root of negative r is then negative, it's the square root of negative 1 times the square root of r. That's I times r. So the square root of negative r is I times the square root of r. Okay? The square root of negative 5 then would be the square root of negative 1 times the square root of 5. The square root of negative 1 would be I. So this is I times the square root of 5. So I can then write any square root of a negative number in terms of I. The square root of negative 4 would be I times the square root of 4, but I know the square root of 4 is 2, so this is really I times 2, or 2I. Okay? Negative 3 times the square root of negative 18, well, that would be negative 3 times I times the square root of 18. I can simplify the square root of 18. The square root of 18 is the square root of 9 times the square root of 2. The square root of 9 is 3. 3 times the negative 3 makes negative 9 times I times the square root of 2. So I'm able to introduce this whole new set of numbers if I just call the square root of negative 1 I, and then I can work with I. Here's some examples. Let's simplify the square root of negative 16 minus the square root of negative 49. These are two numbers that are not real numbers. The square root of a negative number is not a real number. But I can work with them if I use this I thing. So the square root of negative 16 is going to be the square root of 16 times the square root of negative 1. I've got a minus. The square root of negative 49 is the square root of 49 times the square root of negative 1. The square root of 16 is 4. The square root of negative 1 is I. Minus the square root of 49 is 7. The square root of negative 1 is I. I've got 4i minus 7i. I'm going to treat those like terms. I'm going to say that's really negative 3i. I had 4i. I took away 7 i's. That leaves me with negative 3 i's. Number 2. I times the square root of 2. Okay? So I can factor out an I. And I have the square root of 2 plus 3 times the square root of 2. So really what I have is I times 4 square root of 2, or 4i square root of 2. Number 3. Square root of negative 4 times the square root of negative 25. Well, that's really 2i times 5i. That would be 10i squared. 2i times 5i would be 2 times 5, which is 10, and I times I, which is I squared. But I squared, remember, is always negative 1, because that's I times I. Okay? So this is really just negative 10. So I took 2 of these square roots of negative numbers, I multiplied them together, and I got a real number. That's cool. Number 4, I times the square root of 2 times I times the square root of 3. I'll have I squared times the square root of 6. Can't do anything with the square root of 6, but I can do something with the I squared, because I squared is negative 1. So it's negative 1 times the square root of 6, but that's just negative square root of 6, which is, again, is a real number. It's an irrational number, but it's a real number. Cool. Cool. Number 5, 2 divided by 3i. Okay. Well, that looks like I can't do much with it, but really I can, because I, remember, is the square root of negative 1. So this really is 2 divided by 3 times the square root of negative 1. That's a square root in the bottom of a fraction, and I don't like that. So I need to get rid of the square root in the bottom of a fraction. Here's how I do it when it's an I instead of the square root of negative 1. I multiply by 1. But I multiply by 1 in a semi-creative way. We'll call it creative. It's as creative as mathematicians ever get. I'm going to multiply by I over I. Here's what happens. The top is 2i. The bottom is 3i times I. That's 3i squared. So this is really 2i over, what's I squared? Negative 1. So this is really 2i over negative 3. You can leave your answer like that, or you can bring the negative up to the top. Doesn't matter. Negative 2i over 3. That's the same as 2 divided by 3i. I can move the I to the top by multiplying by I over I. Cool. And that makes the fraction negative. Number 6, 6 divided by the square root of negative 2. Let's get it in terms of I. The square root of negative 2 is I times square root of 2. Okay? What do I need to multiply by? Well, I need to get rid of the I. I also need to get rid of the square root of 2. So I'm going to multiply by I square root of 2 over I square root of 2. That'll get rid of both of them. So on the top I'll have 6i square root of 2. On the bottom I'll have I squared, which is negative 1, times square root of 2 squared, which is 2. I'll get 6i square root of 2 over negative 2. I'll cancel the negative 2 into the 6, and I'll get negative 3i square root of 2. That's the same as 6 divided by the square root of negative 2. So I can do whole operations on these new numbers. These new numbers are called imaginary numbers. That's why we choose the letter I to represent them, because it stands for imaginary. They are not real, they are imaginary. Now, why are these useful? Why even bother with them? Good question. Hold on to that question. And let's do number 7 here. The square root of negative 9x squared plus the square root of negative x squared. Okay, let's write it in terms of I. Square root of 9x squared times I plus I times the square root of x squared. So we get rid of those negatives underneath, and now we can work with them as positive numbers. Square root of 9x squared is 3x. This is really 3x times I. Plus the square root of x squared is x. This is really x times I. Okay? That's 3xi plus 1xi makes 4xi. Pretty cool. Number 8. Square root of negative 6y times the square root of negative 2y. Again, let's get rid of those negatives and make them i's. Square root of 6y, I times the square root of 6y times I times the square root of 2y. The I times the I becomes a negative 1 times the square root of 12y squared. Okay, so that's a negative square root of 4 times the square root of 3 times the square root of y squared. Square root of 4 is 2, square root of y squared is y, so negative 2y square root of 3. Now, back to your question. Why are these useful? Why do this? Why make the square root of negative 1i, other than it can do cool stuff like that? Well, it's useful. What if I had this equation, x squared plus 4 equals 0? Looks like a pretty harmless equation, right? It should have a solution. So, what happens if I try to solve it? This is the same as x squared equals negative 4, and I take the square root of both sides, and I get x equals plus or minus the square root of negative 4. But the square root of negative 4 is not a real number. So without imaginary numbers, I cannot solve this equation. And I don't like that. So we make imaginary numbers so that I can solve this equation, and the square root of negative 4 is just 2i. So this is plus or minus 2i. This equation then has two solutions. Both of them are imaginary. You can applaud right now. That's how awesome this is. Second example, 2x squared plus 19 equals 3. Again, an equation that looks harmless. I should be able to solve it. So let's try. 2x squared equals negative 16. Divide both sides by 2. X squared equals negative 8. Take the square root of both sides. X equals plus or minus the square root of negative 8. Again, can't do that without imaginary numbers. But with them, it's no problem. Square root of negative 8 is I times the square root of 8. And the square root of 8 is the square root of 4 times the square root of 2. Square root of 4 is 2. This is 2i times the square root of 2. I can now solve that equation. Pretty cool. Here are your immediate practice problems. 3 problems. Simplify them using i's. That is the end of section 6.6 and 6.7.